9.3 is graphical and numerical methods. So I already recorded a video on slope fields, so you'll see all of the focus on that in that video, and I used the problem set packet. I believe I posted it under the review section of this module, so take a look for that if you want to follow along when you do your slope field. So one thing that I want to highlight, and I think I talked about this in the last video, is that this is another notation for our derivative. Okay, so y dot is equal to capital F of t comma y. In other words, it is the derivative. Okay. So slope field, like I said, is on the other video, so I'm going to skip through these. And we're just going to talk about one example of Euler's method. So Euler's method is a way to produce numerical approximations for a first order initial value problem, right? So basically scenarios where we're looking for just a simple approximation, such as weather prediction, they use this for that, aerodynamic modeling, economic forecasting, but there's much more complicated ways to approximate this. This is just a basic way. Okay. Refer to it the time step. Of course, when we decrease, right, the value of h, or the value of, as that is more accurate in approximation. So keep that in mind as we go through. So this is the only example we're going to take a look at. Use Euler's method with time step of h equals 0.2 and n is equal to 4 steps to approximate the solution of y dot equals y minus t squared, where y of 0 is equal to 3. So initial value of 0, 3. Okay. So we are just looking for numerical approximations for each of the first 4 values here. So I like to organize my information. I like to remind myself that the initial is 0, 3. Right? My h value is 2/10, which means the T1, T2, and T3 that I'll need to do the first 4 are going to be 2/10, 4/10, and then 6/10, right? They work themselves up from 0. If I started with a t sub 0 of 1, then it would be 1.2, 1.4, 1.6, etc. Keeping in mind that f of t comma y is equal to the y minus t squared, right? They're equivalent. Specifically, this y dot is for when we derive with respect to time. It's used very commonly in physics, so many of you are probably even more comfortable with that notation than what we've used here in calculus. So y1, the first approximation, we would need y sub 0, which is 3, plus the step, 0.2, times y sub 0 minus t squared, or t sub 0 squared. Right, we're using the previous values to calculate the current values. So we would get 3.6 here. So for y sub 2, we're then going to use that 3.6 plus the 2/10 remains constant. Then we're going to have the 3.6 minus the 0.2 squared, which is approximately equal to 4.3. Okay. Y sub 3 then uses information from y sub 2, so we use 4.3 plus 0.2 times 4.3 minus 0.4 squared. And that gives us approximately 5.14. And finally, the fourth step, using information from the third step, 5.14 plus 0.2 times 5.14 minus 0.6 squared, 6.1. So you can see that the process is obviously very similar. You're always using information. It's recursive from the previous point, right? And graphically, you can see in the textbook where these points are then connected, and they would represent the derivative, the slope of the tangent line, connecting each of them, right? So that's what this is all kind of connecting back to with our slope field. We would be able to take these values and match a slope field, for example. And the smaller the step, the smaller the h, the more accurate match we're going to have in the end. So the textbook does give a couple more graphical representations to show the difference in time steps. It gives another example where you have to use a calculator, so I didn't include this in this video because for the assessment, you would certainly only be doing it as a non-calculator, simple calculations like this example here.